Okay, so this session of the training will take you to this approach for additive manufacturing, modeling and simulation, and this will tell you about the integrated computational platform for end-to-end AM workflow using AM PravaH. This will also take you to the process of additive manufacturing simulation from multi-physics to multiple scales. By the end of this session, you will be gaining a trust on how and why numerical simulations can be trusted, and lot of investment which is going on the experimental side of AM processes can be significantly cut down by just using the simulations. This is me. My name is Dr. Rimjim Gupta. I am the Senior Applied Scientist at Paanduv Applications. My work centers around developing and applying these physics-based models to make metal additive manufacturing more predictable, more reliable, and more efficient. At the core of this whole effort is AM PravaH, which is a computational modeling software for additive manufacturing. We present to you AM PravaH today, and if we see the length scale of metal additive manufacturing, we go from angstrom level all the way to meter scale. At angstrom or nanometric scale, we have TEM or tomographic information, which will give you the information about phase evolution, crystallographic information. But if you want to perform or gather that information by using the simulations, you perform molecular dynamics or phase field modeling. Although these techniques are computationally highly expensive, but you can get a lot of information about phase evolution by using these techniques. AM PravaH works on a scale of micrometer to meter scale. At micrometer scale, you use synchrotron-based X-ray imaging techniques to have a deep understanding of transient behavior of the melt pool dynamics. And you also perform SEM or EBSD analysis to have a better understanding of the microstructures. Now, if you want to perform simulations to get this information, we do melt pool dynamics, which will give us an entire uh, in-depth idea on multi-physics part of these melt pool dynamics, and which will be a kind of the information that you will be getting from these melt pool dynamics will be analogous to synchrotron-based X-ray imaging techniques. We do microstructure analysis by using Monte Carlo algorithm, and these microstructure evolution will give you a 3D grain evolution analysis and deeper information about how and why these grains are evolving in such a manner, and you can get all the temporal as well as the spatial information about these evolution methods. At part scale, which is a very important scale, again, you can get information about deformations, the stresses generated in the entire part, and the problematic areas. But on top of it, uh, we have these feedstock modeling techniques, because in powder bed fusion you have powder as the feedstock, and how and why these particles are coming from, and what are the characterization of these particles is very important. So the technique that you use for particle manufacturing plays a very important role in mitigating the defects at the initial level itself. Hence, Paanduv is also looking at these aspects of additive manufacturing, which is related to powder manufacturing. Now coming to the primary part of LPBF, which is the feedstock modeling, which happens at micro scale level. Uh, Atomization is one such process which helps manufacturing these particles. There are three categories of these atomization processes. One is inert gas atomization, plasma atomization, and water atomization. Depending upon the cost of these equipments or the facilities, people use all the variety of atomization processes for manufacturing their particles. In inert gas atomization, you have this nozzle wherein your gas with a very high speed, around Mach number 3 to 4, is coming in, and it is impinging the molten metal which is coming from the top. And this forceful interaction of the gas and the molten metal helps to atomize the particles at primary and secondary level, through which the particle formation happens, and these particles are collected using the cyclone separator thereafter. The second part is plasma atomization, where you have these plasma torches which are coming in direct contact of the metal wire. By the temperature over here reaches around 10,000 Kelvin and more, and this high energy process helps uh, atomize the particles, and the atomization happens during the flight of these particles, and we get more spherical particles from these processes. Now, next is water atomization, which is again a low cost methodology to manufacturing the particles. Here, in place of air or in place of gas, you use water as a coolant, and this water uh, interacts with the molten liquid to atomize the particles further, through which primary and secondary atomization happens. Now, how do we implement these processes, and how do we bring these processes live to simulations? For example, here is a nozzle. This is a axisymmetric part that you see on screen. Here is a nozzle, and here from here the molten liquid will be inserted. Now, interacting these air with the molten liquid, the shock waves will be created because these are high Mach number flows and compressibility is accounted for. And you can see the primary atomization where the liquid is uh, separated out in form of the droplets, and these droplets are going down and these particles will be collected further. So you can also evaluate what is the particle size distribution coming out of this. This animation will show you a 3D animations, a 3D representation of the atomization process. And these are supersonic flows which controls the atomization quality. Now there is a clear distinction between inert gas atomization, plasma atomization, and water atomization process. And the thing that we want to look at is the particle size ranges. When we use inert gas atomization process, the particle size ranges from 10 to 150 micrometer, and it is controllable depending upon the speed of the gas that you are providing. Second is plasma atomization process. The sphericity is very high in these processes, as well as the cooling rates. And hence you get a narrow size distribution, which is 10 to 100 micrometer, very spherical particle by plasma atomization process. There are other processes which are water atomization, through which you get a broad particle size distribution. Cooling rates are very high and the powder purity is lower because these are not highly spherical particles. They can be angular, they can be irregular shaped particles also, and which impacts the fluidity or flowability of these particles. Now, as an example, we have shown you when we change the gas pressure from 30 to 50 bar, the particle size distribution also varies. And this distinction and the variation with particle size distribution, you can see by D10, D50, and D90 configurations. Now coming to the next chapter of LPBF. Now we have gotten the feedstock, good quality feedstock. Now we are using these feedstock to our LPBF process and creating these good high packing density particle bed. So PravaH, as already mentioned, PravaH is applicable for laser powder bed fusion, where powder is the feedstock. We also use, or PravaH is also applicable to wire-based laser additive manufacturing, where the feedstock is not powder, it is wire. Similarly, we can also use PravaH to model wire arc additive manufacturing. Again, the feedstock here is wire, and the heat source is also changing from laser to electromagnetic waves, which is plasma. So for the interest of today's session and the current capabilities of PravaH, we will focus more on laser powder bed fusion and wire laser additive manufacturing. The particle modeling for additive manufacturing includes lot of important aspects. Now, the important portion is why these particle flowability is important. We want a uniform powder layering at the end of the day because we want uniform energy absorption in these processes. With high packing density of these particles, this can be achieved. This will also ensure the process repeatability and reliability. It will also reduce the recoater wear and jamming, which is a crucial problem when you use the machine for a very long time. These problems occur. And the typical sizes of particles in LPBF process range from 10 to 50 micrometer. These ranges can also vary depending upon what process you are using for particle manufacturing. But these ranges will help you get the high precision printing. Now, at the right hand side, you see two images. There is one where the particle size distribution is wide, and there is other where sizes are large and the particle size distribution is narrow. Now you can clearly make out these smaller particles will help filling these voids and help creating a better powder free surfaces, which will help filling a better which will help in getting the better packing density of these particles. Similarly, when you use laser on top of it and you create the melt pool dynamics, you will see because of the lower packing density, because of the lower contact surface area between these particles, the porosity will be higher in lower packing density cases, whereas it will be lower in case of high packing density cases. So in order to get a better flowability of these particles, you need to have reduced rolling friction, because fluidity or flowability of these particles depend when these spherical particles roll over each other, and hence the rolling friction needs to be reduced. One other point which is very important is getting a wider powder size distribution, because when you have smaller and large particles in your powder size, there is a high chances that the voids created between the particles can be filled out by smaller particle fractions. Now there is another concept which is in trend right now, when people are using cost effective methods to create these particles. Either you take water atomization process or ball milling process to create these particles. These particles are emerging to be non-spherical. So when you compare spherical particles versus non-spherical particles, there is a high degree of sphericity mismatch between spherical and non-spherical particles, and sphericity is needed to promote good flow and achieve uniformity in higher layer densities, and hence the absorptivity also takes a toll when these non-spherical particles are being used. Along with that, the rolling friction is very high. That's why the flowability is not achieved. However, in AM PravaH, you will see spherical as well as non-spherical particles. We have provided the option for, because people who are creating these particles by cost intensive or cost effective methods, both the ways, they can all use the software without any hassle. These SEM images are coming out from IIT Bhilai, with which we have collaborated for experimental data for non-spherical particles. And you can see from the left-hand side animation, the third layer powder spreading is done on top of the second surface, second layer. And the right topology of the second layer is considered for the spreading of third layer, which is a very crucial phenomena to capture when we do accurate LPBF process. Now, when we switch from spherical particles to non-spherical particles, when we switch from spherical particles to non-spherical particles, these particles can be elongated in shapes, these can be disc shaped, these can be any other shape. So sphericity as well as deviation in these sphericity can ensure that you predict or capture the right size or morphology of these particles. These can also be a different shape of particles mixed together with each other and in a different or customized ratio. So all of these efforts you can test using PravaH to get your accurate melt pool predictions. Now, second part, once we have achieved a good packing density of these particles onto the substrate, the next part is you shine laser on top of it and multi-physics phenomena start happening. And for this, CFD simulations is very important to capture this crucial information from these LPBF process. CFD stands for Computational Fluid Dynamics Simulations, and this is helpful for process modeling of additive manufacturing. Let's take an example of creating this alloy, this duct, air duct made out of titanium 64, and we are using LPBF process to create this particular product. Now, what is the strategy people generally follow? They have the alloy in their hands. They may have or may not have the starting point for process parameter window with them to get a high quality build, and hence they will explore or optimize the process parameters by creating these coupons. They will cut these coupons, they will characterize these coupons, understand the porosity, understand the defects which are being created in these coupons. Once they get high quality coupons, they will proceed further for the part manufacturing. Now, when these coupons are created, a very fundamental phenomena or the building block of these coupons is melt pool dynamics. At a very microscopic level, when the laser is on top of these powder bed, the laser hits the powder bed, the metal absorbs the heat from this laser, and by absorbing the heat, the phase transfer happens from solid to melting. And once the temperature reaches beyond vaporization temperature, the metal can also convert into vapor. And this vapor can play a very important role in creating the defects in this build. And hence, lot of multiphysics is happening at the same time. Surface tension plays a very important role in deciding what will be the final build look like and what will be the behavior of the melt pool. Apart from that, the thermal behavior of this alloy will also play a very important role, whether the defects will be created or not. And hence, to understand this phenomena, we need a CFD modeling software which can help us understanding the nitty-gritties of these processes. Now, before going further, it is important to understand what are the responsible forces for this melt pool to happen and fluid flow to happen. When the vapor is ejected out from this system, it impinges a recoil pressure onto the substrate, which is onto the liquid metal, which is in the downward direction. The gravity also acts in downward direction. The buoyancy force acts in upward direction because it is an upward thrust that is applied onto an object which is into the liquid. And the surface tension, which is a very important phenomena, it acts as a driving force for the fluid flow to happen. Because the laser is at this point, the temperature of this point will be much higher than the surrounding areas, and hence the liquid have a tendency to flow from low surface tension areas to high surface tension areas. And the temperature which will be higher at this region, the liquid will have lower surface surface tension in this region. Hence, the circular flows will happen in this particular area, and which will ensure if the fluid flow is happening in right direction or not. Now, we take a case of keyhole formation, wherein from this particular area, from this emptied area, the vapor is ejecting out, and which forces the liquid to move downward, and which acts in downward direction. The recoil pressure acts in downward direction, and it helps to open the keyhole from all the directions, whereas the surface tension force helps to uh, collapse the keyhole. So these forces are acting in opposite direction, and this is very important to understand the balance of these surface tension forces as well as the recoil pressure forces. Apart from that, recoil pressure is also very important because a very fast vapor plume ejection, which almost reaches a speed of 10 raised to power 2 to 10 raised to power 3 meter per second, and it creates a friction between the liquid and the gas phases, which produces the shear stress at the interfaces. Hence, the the accurate prediction of the vapor phase is very important, and hence with the help of AM PravaH, we use four phases into the system. Four phases being the solid phase, the molten phase, the vapor gas phase, and the shielding gas phase. So all of these four phases are simulated and tracked at all times, which ensures the accuracy of the system. So I'm showing you some of the snippets of the simulation that we have done previously. This is the particle spreading. Beneath this, there is a substrate and providing us a right set of the particle variations, which starts from 25 microns to 45 microns in radius. We get this dense particle bed. Now, when we take this domain to computational CFD domain, we get something like this. And the primary aim of CFD is to compartmentalize this computational domain into different volumes, fine volumes, and which is called meshing. So we have this computational domain. On top of it, there is a shielding gas. On the bottom, we have solid. Whatever you see in the dark gray color is the solid, and this is the meshing that we have created. Now, once we solve the Navier-Stokes equation, once we solve the governing equations, which is going at the back of the solver, we get the thermal distribution, which is shown here. And there is a lot more information that you get by using the CFD simulations. Now, in this top image, which is a keyhole formation, you can see the four phases distinctly. This is the liquid phase. The gray color is the solid phase. The vapor is ejecting out from this region, and the remaining is the shielding gas phase. So all the four phases, you can quantify these four phases at any time, at any space. Now, before proceeding further, it is important to understand what are the governing equations to solving these problems. The first equation that we use is the continuity equation. Although the continuity equation is the mass cannot be created nor be destroyed, at any steady state, the mass which is coming in will be equal to mass going out. And hence, we take volume fraction because we are using multi-phase phenomena. Volume fraction is a better quantity for analyzing these flows. And hence, the second one is momentum balance equation, which is also called the Navier-Stokes equation. We use effective density and effective viscosity to analyze these problems because these are VOF based methods. We solve for effective density and effective viscosity. The source term, okay, I'll talk about the terms separately. This is the unsteady term, which is the change in momentum with respect to time. This is the convective term, which is responsible with the velocities happening into the system, into the fluid flow. This is the diffusive term. This is the pressure gradient term. And these are the force. This is the gravity related term, and this is the force which is happening because of the surface tension. And now this surface tension, which is changing with temperature, and accounting that information is very important. So this surface tension can be characterized with the Marangoni convection term as well as the tangential surface tension that we have applied, which is because of the curvatures in the system. And apart from that, the phase change term is again very important. We use Lee model to mimic that in AM PravaH. So The final outcome from this slide is that we are using four-phase multi-phase system with accurate phase change model. The temperature dependent properties is something which makes the overall system more accurate, and you can deploy these temperature dependent properties of different alloys into the system. The surface tension forces and Marangoni convection will decide the fluid flow behavior, and we have accounted explicitly for surface tension forces. Now we come on to a very important part of LPBF, the parametric dependence of different parameters onto the fluid flow behavior. And what are these parameters? We go one by one. We have laser power, we have scan speed, we have spot dia, and we have Fresnel coefficients. Now coming to the laser power, depending upon the power that you provide to the system, it will it will decide how much heat is being transferred from your laser, from your heat source to the metal. And depending upon the absorptivity of your alloy, it will decide how deep the melt pool will be created. So changing the power of the laser will increase the depth of your melt pool. If the laser power is enhanced further, it may also lead to defects such as keyhole pores. Scan speed is another criteria through which you can control your defects. The lower the scan speed, the higher the width and the depth of the system. The higher the scan speed, you can control uh, the defects of your system. Spot dia is another feature which is important. If you have a Gaussian spot of your laser, the D4 sigma, which is the 95% confidence interval of that Gaussian plot, will be considered as D4 sigma, and which the PravaH software takes into account for modeling the system. Next is Fresnel coefficients. Why these are important? Because when the light goes and interacts with the metal, the laser metal interaction happens, it can create, once the vapor is formed, it can create the recoil pressure, and these depressions can happen. Now when these depressions are happening, this laser can interact further from the keyhole, and it can reflect multiple times into the system, which causes severe effects like deepening of the keyhole. And accounting for the Fresnel coefficients is very important into the system to mimic the right uh, melt pool dynamics. And these coefficients can vary according to different alloys. For example, copper, aluminum have high reflectivity, and hence the reflectivity is higher, Fresnel coefficients can be lower. And these different interfaces, such as uh, your liquid vapor interface, liquid solid interface, liquid gas interface, they will have a different values of these Fresnel coefficients. So understanding this phenomena becomes very crucial. Now coming to other parameters, which is preheating temperature. Now we all have heard that the temperature gradients in laser powder bed fusion are very high. These go up to the range of 10 raised to power 6 to 10 raised to power 7 Kelvin per meter. That happens because of the rapid melting and solidification into the system. Exactly where the laser is, the temperature will be very high, but if you go across different lengths, the temperature deviations or temperature difference becomes very high, so that temperature gradients are even higher. And hence the resolution to that is, you can preheat your system, you can preheat your substrate by and that will change the temperature gradients occurring into your system, and which will eventually mitigate the defects. You can provide these all information in PravaH. You will see the graphical user interface in the next session, and there you will be able to correlate with all the concepts that we have. Chamber pressure, again, it is a very important uh, parameter that people have not identified yet. When you have an ambient pressure in your system, you can get even higher keyhole porosities, because the liquid have a tendency, the vapor has a tendency to go from higher pressures to lower pressure. When these pressure differences are higher, the vapor will be taken away more efficiently, and at same time you can see when the pressure is ambient pressure, which is 10 raised to power 5 Pascal, versus when the pressure is 10 raised to power pressure is 1200 Pascal. The defect location is changing, as well as the deepening of the keyhole is also changing. The keyhole is deeper in case of the first, and the keyhole is smaller in case of the second. So controlling the chamber pressure can help you mitigate the defects even further. The next point is shielding gas flow. If you have the shielding gas flow in particular angle, particular direction, particular velocity, you can eliminate the defects, because it can take away the vapor from there and it can help mitigating the defects further. Now part, another parameter which can be controlled is scanning strategy. People have been optimizing these scanning strategies from a very long time. They are using unidirectional tracks, they are using bidirectional track, island strategies, and several other zigzag patterns at different angles to optimize the scanning strategy to mitigate the defects such as porosity and controlling the microstructure of these systems. You can see this example from literature we have taken. They have printed multiple coupons using the same set of feedstock, and they changed the scanning strategy from unidirection to zigzag direction and to the island directional. And they have achieved a control on the microstructure formation through that, as well as they have been able to controlling the porosities with these scanning strategy. The texture of the microstructure evolution can also be controlled by using these controlled scan strategies. Now we come directly to why PravaH is applicable and up to what scale you can model these CFD simulations. These are very high fidelity simulations. That's why the scale can be as low as a single bead analysis. This is a single bead analysis. You can go up to multi-track. You can go for multi-layer systems. You can go for different scanning strategy such as this one. And you can also customize any sort of scanning strategy, go for even higher layers of number, and you can go up to multiple layers, as much as 30 layer we have simulated, but other users of PravaH are going up to 100 layers and 200 layers also. But when you go from smaller scale, from smaller scale of the melt pool dynamics to higher one, you will lose lot of information, because you will get information such as lack of fusion defects, but the fluid flow and the minutest details of the single bead analysis, you will not be able to understand by doing directly the multi-layer simulations. So it is very important to start from the building block of the melt pool dynamics, which is the single layer analysis. These are some examples that we have modeled with PravaH. The first example is aluminum based alloy. This is a steady state. This is a conduction mode melting and solidification that you see on screen. As the laser progresses, you can see a yellow spot which shows the higher temperature in that region, and the surrounding liquid is red, that shows that the temperature of the liquid, molten liquid, is lower in those regions, relatively lower in those regions. We have also used the ray tracing methodology to have a better visualization with the post processor that we use. The bottom one is a single layer high fidelity simulation through which you can see all the vectors coming out and moving in back and forward direction, which shows the molten fluid flow in this single bead analysis. You can also see some partially melted powder at this region. Apart from that, not only single bead analysis, you can strategize, you can change your scan patterns from single bead to zigzag patterns and to any complicated shape that you think can eliminate the defects in your system. Single layer analysis are easily possible in PravaH, but the complicated part, which is the multi-layer analysis, is also feasible to do in PravaH. The example that you see on screen is for 30-layer simulation for alloy, which is Ti64. Now, what is the outcome of PravaH? What information can you gather from PravaH? So you can visualize all the defects that you can have, which is primary defect in your system can be keyhole formation, and these keyhole information, which is the bubble sizes, which is the rear wall angle, front wall angle, this is very much possible by using PravaH. The gas induced porosity, or you can say uh, when the particle packing density is not high, the lower packing density, and there is air between the particles, and that can induce porosity into the system, and that porosity you can quantify easily because of the high uh, intensity, high energy of the laser. The liquid spattering happens quite often, and these liquid spattering can be captured very well because we are capturing the laser material interaction in high detail. Now, when you do CFD simulations, you get the information about velocities, about pressures, about temperature. In-depth understanding of temperature evolution in the entire part will help you gain understanding if you leave a thermocouple at any point in your system, how the temperature will be evolving. So you can get the information about thermal cycling plots at any point in the system. And these thermal cycling plots can also be revealing the information about the cooling rates, about the temperature gradients in the system. Now, so far we were using Gaussian beam lasers, but now, because we all come from the research field, and industrially this has not been feasible to use different shape of the lasers. It is not available in the market, but at the research level, people are exploring the concept of laser beam shaping quite extensively, and simulations are the best way to explore that capability. That capability PravaH offers you in form of you can customize your laser shapes to anything. This is an example of laser beam shapes from elliptical to basal function to Gaussian beam to top hat beam to multi Gaussian beam and to the ring beam shapes. And by changing these distribution, heat distribution in these different shapes of the laser, you can control the microstructure, and also you can control the defect formation in these build parts. There is an example that uh, we have validated with the experimental results. This is a Nature article publication that we have taken for bare aluminum plate. The laser power here is 500 watt. The scanning speed is 1.2 meter per second, and the spot dia is 50 micrometer. And you can see at the beginning of the melt pool itself, the keyhole is unstable keyhole. There are pores created successively as the laser moves from back to forward direction, and there is a clear ejection of vapor happening in the system. We have modeled the similar system, and we have seen the evolution of keyhole as well as the progression of keyhole in the similar manner. As the keyhole moves further, it leaves lot of pores behind, and it leaves the vapor depression at the end. A persistent keyhole can be seen from start to end from the top view in this animation. Now, At different time interval, we have taken the front wall angle experimentally, is it is provided in the literature, and simulation results we have obtained which are in close agreement with the uh, experimental results. The front wall angle is quantified to be 85 experimentally, and the average front wall angle is 83 in case of simulations. The average keyhole depth is also matching quite well with the experimental results. Now, when we develop high grade builds, it is these industries are specifically aerospace industry where we need high density parts. Now, how do we quantify density with using PravaH? We are able to understand the thermal effects, we are able to understand the fluid flow, but how do we quantify the important parameter, which is the density, or what is the porosity in the system? So for that, it is recommended and it is advisable for people to do multi-layer simulations, which will give a better idea on what is the network of pores look like in the system. As we do experimentally, we cut down the rough edges of your volume, and then you perform your experimental analysis for porosity. In the similar way, we cut a portion of volume in this part and we quantify what is the density in that part, and that way we calculate the porosity in the system. For this particular case, experimentally the porosity is reported to be 0.55, and porosity by simulations we achieved 0.63%. Now moving ahead from laser powder bed fusion to wire based laser additive manufacturing systems. Here the feedstock is wire, and wire is interacting with the laser at all times. Wire is at a certain angle. With the scanning speed, with the feed rate of wire and the clearance provided between the substrate and the wire, you create these elongated structures, and these are used for high scale build processes. Now, there can be multiple defects occurring in wire-based TED processes, which can be non-uniformity in these builds, which can be vapor entrapment, which can be humps, right, like this, which can be this lack of fusion defects between the layer, and lack of integration, delamination between the substrate and the bead. So these are some common defects which are occurring in DED processes, wire-based DED processes, and PravaH can help you mitigate these defects and visualize these defects when you use certain process parameters, and PravaH will help you optimize these process parameters to the best. This is an example. This is a validation that we have performed against the experimental experiments. This experimental data we have received from Harbin Institute of Technology, and we have performed the simulations, and I will also show you some a comparison between the experimental and simulated results. So when the process parameters are varied from for different feed rates, you can see the liquid mode transfer changes completely from droplet transfer to continuous liquid transfer, and that we have also observed in the simulations that we have performed. The further quantification can happen with respect to what is the contact angle between the substrate and the bead formation. So when the laser power is varied from 1200 watt to 1800 watt, we have seen, we have compared the contact angles with experimental data, and we can say with surety that these are in good agreement with the experimental uh, data that we have achieved. Similarly, we further compared the energy density versus width, depth, and the height that the experimentalists have achieved with respect to the simulations. When the laser power is varied from 1200 watt to 1800 watt, you can compare the width, the penetration, and the height of the of the bead. The error percentages for height, for depth and the width are below 7 to 8%, which is quite reasonable in case of WLAM processes. Now coming to the another simulations that we do for other process of metal additive manufacturing, which is wire arc additive manufacturing. These processes are used to create larger build parts. They have microstructures up to millimeter scale. They have melt pool dimensions up to millimeter scale. So these are high scale parts that people create by using wire arc additive manufacturing. Here you can see a different liquid transfer methods which are happening either by droplet transfer or by continuous transfer. And the defects occurring in these systems can also be quantified very well. This is another validation that we have done for WAM. The reason why I'm showing you the validations, because we want to build trust for you to do numerical simulations for metal additive manufacturing. It will build the trust for numerical simulations, and hence it can efficiently cut down the investments and the time and the resources that people are investing right now on the experimental side of things. So this particular case is done for Ti64. The process parameters are provided below. The arc voltage is 25 watt. The arc current is 220 ampere. The wire feed rates are in the range of 1 to 5 meter per minute, while speed is 4.5 millimeter per second. And by providing these data, you can see the bead formation. Right there, you can see the temperature evolution and Q, which is the in watt. You can quantify that, and you can see how we have achieved the width and the height of this particular bead. This is compared with experimental results and are in good agreement with the experimental data. These are the snippets at different time steps, different times of this particular animation. Now coming to the next part of EM simulations, we have been able to understand that why CFD simulations are important. And these are at a continuum scale, which is micrometer scales we are operating. Now these microstructures are inherent structures that are evolved in any material. And these are very important to understand. These can be changed by different thermal experience to the material, and depending upon the solidification rate, these evolution processes can be changed. Now you know that in laser powder bed fusion we have temperature gradients ranging from 10 raised to power 6 to 10 raised to power 7 Kelvin per minute, and because of the rapid heating and solidification processes, these microstructures are evolved in these systems. This is a 3D representation of the grain evolution in this process. Now, apart from the 3D information, what you can do is you can cut down these sections and at different time and different locations, and from which you can have a voxel size information and grain evolution information, that in which manner the grains are being evolved. You can correspondingly have the information about crystallographic information in which particular direction the grains are being evolved. Furthermore, so far in the software, we are using Rosenthal-based equation to get the heat evolution or thermal evolution in the build parts. But now we are correlating the macro scale modeling to the microstructure analysis to gain the accurate thermal history, so that the accurate solidification can be modeled, and furthermore we can get the correct evolution of the grains. The microstructure physics will be covered in tomorrow's session, but I can tell you that we are using Monte Carlo Potts algorithm to model that. Now, this is a case study that we have performed. The alloy here is SS316L. This data is coming from one of my colleagues, and the melt pool dynamics, melt pool shapes are quantified, and corresponding to that, we have created a single bead analysis for melt pool for microstructure evolution. Now we have this single bead information. With this single bead information, we have extended further to multi-layer, multi-track systems. So now we have 5-layer, 4-track systems into the microstructure analysis. Now the interesting part here is at the end, at the corners, you see smaller grain sizes, but at the middle, you see much larger grain sizes. Why this is happening? Now, we have provided a particular hatch spacing to the system, because of which the remelting is happening at the center part. Multiple times, the same solidified metal is melting again and again, and due to which these grains have become much larger and grain coarsening has happened, which effect you will see from the grain size evolution that the software generates. Similarly, you can cut different sections at different height, and you can see how the transformation of equiax grains happens from that to the columnar structures. This is a further methodology to visualize these results. You can cut different portions, different sections, and visualize in which direction and how the grains are being evolved. And you can also have corresponding information about the crystal directions. This is another validation that we have included. This particular simulation is done for SS316N, and the literature is reported here. This is the optical microscopy image that we have uh, provided. Corresponding to that, we have EBSD analysis also here. Now, with these experimental data, we have simulated with using PravaH, and you can see the dark spot here, which is the density plot we have created. The dark spot here represents that there is a density compromise in this region, which can also be validated by the optical microscopy, which is reported here. There is a hole, there is a pore at this location, which can be ensured by the results that we have generated with PravaH. Now, corresponding to this thermal history, we have taken this thermal history to the microstructure evolution method, and we have created this microstructure, and we can see the location of these fine microstructures is matching exactly with the experimental EBSD data. In fact, the larger grains evolved in this region is also matching with the experimental data. This is the macro scale modeling. The bubble is rapidly created and evolved during the process. And once we create the density plot, we have seen a dark patch which shows that there is a compromise in the density happened in the system. Now, there are a couple of other validations that we have performed. These ones are for Ni200 alloy, and this one is for SS316L. This is the cross-section, experimental cross-section EBSD image, and this is the simulated one. The location of the fine grains versus coarser grains matches with the experimental image. Similarly, the evolution of grain pattern in this image for Ni200 is matching closely with the experimental image, which shows that qualitatively it matches quite well. But qualitatively is fine. We have further analyzed it quantitatively. We took this data, we created a plot with the grain area, grain length, and the grain angle. And we have found a close correlation between the experimental data with the simulated data. Now, last but not the least is the part scale modeling, which is again an integral part of additive manufacturing simulations. And these scales are going beyond millimeter scale up to the meter scale. Now, we have this example where you have this thin plate. The build single bead analysis done over and over again, and this build plate, this thin plate is created. You can see and analyze there are deformations happening at the edges as well as in the middle, and these are the corresponding microstructures optical microscopy plot that is provided. And for this, we have also simulated the microstructure, 10 layer microstructure. You can see the top view as well as the side view, and grain merging happening across the different layers because of the remelting. Now, corresponding to this 10 layer structure, we have analyzed what is the stress and deformation analysis, and you can see at the edges and at the middle there is a clear effect of deformation. Similarly, we have also understood the effect of different orientations on displacement as well as the stress analysis. When you change the orientation of this particular hexagon screw from 0 degrees to 45 degrees to 90 degrees, the stress emerge is quite differently from each other. Similarly, the deformation analysis says supports this analogy. So, in a nutshell, what PravaH can do in metal additive manufacturing? It can solve the melt pool dynamics effectively for these processes. It can predict the microstructure evolution with dynamic temperature gradients. It can estimate the crystallographic information and the grain sizes, and these grain sizes you can correlate with the analytical equations, which is Hall patch equations, which will be covered in tomorrow's first session, and they will take you to the mechanical properties of the build part. The next is it can also simulate the deformation and stresses for the component, and it can model and simulate across different length scales. So PravaH, we have presented to you PravaH, which is an all-inclusive computational modeling software for additive manufacturing. PravaH is developed, licensed, and maintained by Paanduv Applications. It is an indigenous effort. This is a Make in India product, and we are located at Bareilly, Uttar Pradesh. This is our office from which we have connected with you. You can contact us at support@paanduv.com, and you can write to us, visit us at any point. So the final outcomes, what you can get from PravaH, final benefits of PravaH is you can perform end-to-end simulations, you can cut down the cost by 67% in initial process optimizations, 20 to 30% saving on material costing, and it can also reduce the rate of failure to 10%. It can save lot of experimental trials and characterization, and it is emerging as a digital twin for additive manufacturing process, because we are covering end to end metal AM evolution process, starting from metal powder building to all the way to part scale. Thank you.